So hopefully you've all seen that that I posted the homework sets for the first or the problem set for the first homework. Like I was explaining, this will be problems from the book, so exercises from the book. So that should be very straightforward. If you get into trouble, of course, you can hang out at office hours, and then we can go over it, or I can try to see if I can help you without, of course, giving you the entire solution. So that's part one. Part two is because I was a little late posting it, I pushed the deadline or due date for that. So I believe it's due 1 week from now, and I posted it on Saturday. I think, was it Saturday or Sunday? Anyway, Sunday. And then so that's logistical stuff. Now let's get to the actual fun parts. So we're actually starting proper electricity and magnetism. We've of course done the intro a little bit, but now we're going to do this for real. Keep in mind that for now we're doing electrostatics, which means that we're assuming that charge configurations are stable. Things are not moving, even though we will at some point have imaginary processes where we'll move one charge closer from infinity close to some charge, and we'll get a potential energy. But we're assuming we're doing that all quasi-statically, and that whatever transient phenomena like induced magnetic fields and radiation, that they have all ebbed away, and we're just comparing before and after states. That should be enough of a thing to get us started. So hopefully that'll be okay. But just keep in mind that sometimes when we write down that the curl of E is 0, that's really only the case when nothing else is moving. So we'll do that. I do think that we can do these two chapters. Sorry, this chapter in the next two classes. So yeah, so that should be all right. Okay. All right. So so we're starting with our basic electrostatics, and our basic electrostatics always starts with the Coulomb Force Law. So let's start there, and we'll start slow, and then we will pick up the pace. So Coulomb's Force Law. I don't know why I was writing force law. It's not quite the same. Okay, Coulomb Force Law. So Coulomb Force Law, obviously, got two charged objects. You got some Q of 2, you got some Q of 1, and there's a Coulomb force that is acting on this charge. So it's the force on Q2 due to the object number 1, and it's equal to that product of Q1, Q2 over R12 squared. And actually, let me do this consistently, because otherwise the indices get a little messed up. So 2(1) squared, and it is pointing in that unit vector R21, where R21 is, of course, the position of 2 minus the position of 1, which means it's a vector that is pointing from 1 to 2. So this is R21. All right, and as per usual, using the unit vector notation, sometimes it's useful to just kind of write this R21 squared, cubed, it's the entire point, R21 vector, right? Because we know that for any vector, that a unit vector is a vector over a length. Okay, so that's all I did. And then, so that R21 is, of course, the length of that same vector. I'm sorry, I'm doing this a little bit sloppy. I have to fix a couple of things. Okay, so this is R21 vector. So there you go, R21 vector. Okay, so I think I got everything right now. Yeah, so R21 is a scalar, and everything is good. Okay, units, because we're doing we're using the Gaussian system. So the units of charge are ESUs, or electrostatic units, or stat coulombs. And you know, 1 coulomb from, you know, the SI system is 3 × 10⁹ ESU. So for reference, does make life a lot easier. And then of course the force also has a different unit, and it's dyne something, and I never remember what it is. So I'll usually just look it up. Okay, but the beautiful thing about doing using this this unit system is that, of course, there's no 1/4πε0 here, so it does really clean up all our math a lot. Now, we usually take electrostatics problems and tease them apart, where we'll say, okay, so rather than considering a situation where we just have a bunch of charges and they're interacting through Coulomb forces, we usually say, well, let's say we have n charges, and we're adding 1 to the problem. So let's say we have n charges, and we're adding 1 to the problem. So we're going to do n+1 charges. And the question is, what happens to that last electron or charged object that we added to the problem? So then what we do is, well, this extra object will experience some kind of a force that is, it's the same Coulomb force, but it's going to be the charge of that n+1th, is that the thing, n+1th object, and then place it in an electric field that existed before we added this last charged object. And then of course this the origin of those that electric field is due to the n charges that we had arranged before. And of course this is now a this is an inductive problem. So for instance, you could then figure out, okay, how did you get the nth charge there? Well, you had n-1 charges, and you placed another object in it, and then there was a Coulomb force as a result, right? So, but it's important that you realize that this electric field exists even before we place this little q in it. Furthermore, we are assuming that little q is a test charge, and therefore there's no there are no induced changes in the rest of the system. Okay. All right, because otherwise, if you place this thing here and then the other charges get moved around a little bit, then we're not talking about a well-defined system. Okay, so that's our setup for the electric field. So therefore, we have the electric field, and we have the electric field of a point charge. Point charge, let's call it Q to make things really complicated. So this is a point charge, it's not a test charge. That electric field is going to be a function of where we look at it, obviously. Okay, it's going to be a function of R, and it is Q over R squared R hat, or of course Q R vector over R cubed. Okay, and that is if we place this thing at the origin, And if we shift our coordinate system, so we place, instead of having the point charge at the origin, we place it at some. So we're doing the same thing, right? So same setup. We are placing it at some position R prime. Then the electric field in that position R is Q. Now this this R is a little bit more tricky, right? So this is now R minus R prime modulus cubed. Okay, so it's the same situation, but we've shifted our origin, if you want to think about it that way. And that's of course for a single charge. And now we can do multiple charges. So for instance, multiple charges. And by the way, something about language, I'm kind of sloppy. I always say multiple charges. Obviously, what I really should be saying are point-like object with a charge Q, or point-charged objects. So that's my shorthand. Just, you know, charges are not a thing. Charges are a property, but okay. Okay, so charged objects, multiple charged objects. Okay, so then our electric field in some position A is the sum over all the other charged objects that we indicate with an A. So that's our counter. So from 1 through n. And we'll take our QA, and we will need to figure out what that vector is that's joining the position to the position of interest. Okay. Now this should all still be quite straightforward. Any questions so far? Okay, so that's the problem that we'll do on nearpod. So instead of doing continuous, we'll do it this way. Just helping some of you along a little bit. All right, let's work this out. So E of R. Hang on. Okay, so the tricky part is figuring out what's happening with all of these things under the hood, right? Because this is, as you've noticed, is quite a compact expression, even though it looks a little baroque. It is quite compact. We're using vector notation for everything. Now the way that this collapses into a surface integral may not be easy to see. So it helps to be able to walk through one of those exercises. So obviously sigma here is surface charge density. So we're getting the surface charge density. And then anytime we encounter a z prime when we're doing our integral, we can just swap in a 0, because this is a charged plane at z is equal to 0, spanning the xy plane, basically. So we can write this out. So it's a triple integral. So sigma delta z prime, and now we'll do x. Oops, let's do it like this. X times x minus x prime plus y hat y minus y prime plus z hat z minus z prime. Okay, and now we're getting here x minus x hat prime squared plus y minus y prime squared plus z minus z prime squared, okay, raised to the power 3/2. And now we're still integrating dx prime, dy prime, dz prime. Now, all that happens when we integrate a way that z prime is that this thing goes away, becomes a 0, this becomes a 0, and that z integral goes away. Okay, so remembering this definition for integrals with a delta function, if we have just a delta of some x, you basically get that function's value evaluated at that point 0. What is that function? It's basically everything here that does not involve a z prime, right? Because then we just set it to 0. So we drop one of the integrals and we are left with our sigma. We still have our x hat, x minus x prime, and our y hat, y minus y prime. And now we still have our z component. That's the thing that's going to give you an electric field in the z direction. So you need to keep this. You cannot drop the z term because the field is definitely going to have a z component. Okay, and then here we have x minus x prime, y minus y prime, plus z squared, right? Because prime is 0, 3/2, and then dx prime, dy prime. All right. So that's what it looks like in 2D. So this should be a familiar form, but you usually have when you do these kind of integrals, you usually do this in for planes that are infinitely large, and then you convert this into an integral over polar coordinates. So then instead of a dx and a dy, you integrate over an r and d theta. And then the nice thing is you pick up a vector r here, and then all of a sudden you can actually execute the integral. Otherwise, it becomes a little hairy. Okay, so so similarly, we can do linear charge density. So for instance, we can say r minus r prime lambda, and now we're putting this at this is basically a thin charged wire or wire on the z-axis. Actually, it's not on the z-axis, it's parallel to the z-axis. Parallel to the z-axis. If it's on the z-axis, then you should, again, drop these things out. Okay, and then finally, of course, the this one, delta x minus x prime, y minus y prime, z minus z prime. That's a charged object, charged point-like object, if you want, point-like object at x prime, y prime, z prime. All right. So that's how your delta functions work out. Oops, then this of course needs to be Q. Okay, so units. This is linear charge density. So this is per meter. This is just charge, and the sigma is per meter squared, and rho is per meter cubed. Okay, so we've talked about the electric field of a point charge. We talked about the electric field of a distribution of charged objects, and therefore also about charge distributions. this is all, this should all be very clear. And then we're getting some kind of an electric field, but that electric field of a point charge we can write as E is minus the gradient of that charge divided by R. And that's easily verified, right? So if you have the gradient operator in spherical coordinate system, so for instance, it's just 1 over R ddr, right? So you pick up a factor R and a factor minus, and then now you get the electric field. Okay. Now this is the famous potential where phi is the potential of a point charge. Okay. So it's of course the potential of a point charge located at the origin again. So if you want to generalize this, we can generalize this a little bit. Where is my here's my description. So we could do the same thing, right? So if instead of writing this in terms of an electric field, we can write it as the sum of the potentials due to those charged objects. And then instead of having to add vector quantities, we can add scalar quantities, and then in the end, we can get our electric field back. So if you want to go to a set of point charges, oops. So let's say column QA, where A is just some kind of an index that runs through it, then the potential at some location R is going to be the sum over all those objects. So we're summing over all those objects A, and then all we have to do is I should have written this a little bit higher. All we have to know is what is the distance from that point R to the location of that object A. My eraser's again getting a little dirty. Okay. And of course, that's for a set of point charges, and we've done this for a set of point charges, but now we can do this for a for charge distribution. We get our phi of R is, so instead of doing a sum over QA, we do the same thing. We have now an integral over some charge distribution rho, but now instead of summing over A, we're integrating over the position R prime. And oh, I keep writing this too low, sorry. So, and that is R prime. And again, we just need to know how far away that is from the point of interest R. And we're integrating over over the primed volume elements dx, dy, dz, or written in this way. Okay, and then in the end, that's your charge distribution. You get some potential. Obviously, it's easier to get the potential than take the gradient and get the electric field than doing this whole thing starting from the electric field. All right. Now, so we talked about that. So let's say there's some electric field, you know, some kind of an arbitrary electric field, And there are lines here. And these electric field lines are the tangents. So locally here, there's an expression in the book that's nice to use. So there's a tangent here that is called dr vector that is parallel to E. And in fact, E vector over E is that dr vector over ds, where ds is an arc length that is measured along the object as it's curving. Okay, but that's not what I wanted to get to. Now let's say, so I have some electric field, and this electric field is it's otherwise static. We're going to do stuff in this field, but we're assuming that we're not altering this charged field configuration. So let's say we have some kind of an object here, so some Q, and we're going to take it from a position. Where'd my marker go? So from here to there. So from position 1 to position 2. All right. So take our path like this. So take the green path. Then the work done in doing that is just minus Q times the force integrated over distance, right? So Q times E is the force, so that's going to give you E, and now that's R, and we're dotting that with DL, where DL are those are the infinitesimal sections DL vector here. So we're at every point here, we're evaluating the dot product of DL with E, and we're just integrating that. Okay. Now, with the definition of our electric field is as the gradient of our scalar potential, we can just plug this in, and we get Q times the gradient of phi, and it's gradient of phi integrated over that length L. And by definition, this integral is Q times the difference in the scalar potential at the end position minus the scalar potential in the starting position. So this integral goes from some point 1 to point 2. So it goes from point 1 to point 2. And of course, that's our potential difference. So that should give you pause. The fact that you can write this, it should be familiar to you, but it should still be something that hopefully you will not take for granted. So this work done in moving this charged object from position number 1 to position number 2 is only a function of the beginning and the end points. Sorry, these are vector quantities, obviously. So delta W is independent of the path taken. Okay. And therefore, the electric field is conservative. And that also means that if you take a closed path through an electric field, that needs to be 0. So take this 0, right? Because that EDL, if it's a closed path, is basically a start point and an end point that are identical. So that means that the potential here is equal to the potential there because the positions are the same. So therefore, the this circuit integral through the E field is 0. So that's the same as saying that the electric field is conservative. Of course, you should recognize this as Faraday's law or the circuital law. Sorry. So this is the Spherical law. Or Faraday with dB dt is 0. Okay, so no time varying flux. Also no moving wires, but that's fine because we were doing this all in static fields. Okay, so so then we can ask ourselves, okay, if that's the work that's being done, in the end, if the work being done by moving this charge object from here to there is positive, and then we let it go from here to there, obviously we can change the potential energy by moving a charge object through an electric field. Now, again, the most simple system for starting this with is just again our two charged objects. So our charged object, let's call this one number A and number B, and they are separated by some distance RAB, and then our potential energy for this configuration, just for these two charged objects, is the product of the two charges divided by the distance between the two charges. And of course, the way we got here is by taking the work integral through an electric field due to one charge. So for instance, you could move QB into position through the field due to QA. And then doing that work through that field just means that you have to do that line integral, which means that it comes down to the potential. So all you need to do is take the potential of that charged object QA and then evaluate that potential difference between an object when it's very, very far away, where the potential is 0, and then somewhere close where the potential is QA over whatever that distance is, and the product is the potential energy. So there you go. Now, you can build any kind of charge configuration by considering pairs. So for instance, if you have for a set of charged objects, point-like objects, the total potential energy, sorry, I did not write, this is potential energy, obviously. That's potential energy. The total potential energy is the sum over all the pairs of QA, QB over RAB. All right. Now, what does that mean? Sum over all the pairs. Let's be explicit about it, because this is the point where we need to start really paying attention to how many terms we actually have. Okay, so let's say got on object 2, 1, 2, 3, 4, 5. Okay, so we've got this configuration of 5 charged objects, and we want to know what the total potential energy of this system is. We have to consider the potential energy due to the sum of all of the pairs. What does that mean? Well, you start with this object number 1, and you say, okay, which of these charged objects are considered forming a pair with charged object number 1? That means you're going to go add 1. You're going to pair it up with 2, 3, 4, and 5. Okay, then you're going to take 2, and you're going to say, okay, which other charged objects would together constitute a pair with 2. We're going to skip over 1 because we already counted at 1, so we just do 2, 3, 4, 5. And now with 3 forms a pair with 2 and 1, but we already had those because the potential energy is symmetric under the exchange of 2 objects. And then, so this one forms a pair with number 4 and number 5, and then finally 4 forms a pair with number 5. Okay, so a sum of pairs here is actually, it's two sums, right? So it's a sum of, let's call it A from 1 through n minus 1, and then another counter B that goes from A plus 1 to n. I think I got that right. Yes, that's Q A Q B over R A B. So pay very close attention to the indices, right? So that's what I was doing here. So A started off as 1, and then B started off at 2 and ran all the way to n is 5 here. But A didn't go beyond 4, right? Because if we're at 5, there's no more things that it can form a pair with. So that looks good. Okay, so now my question to you is, how many terms are in this sum? And I'll let you think about that for a little bit. All right. Hopefully you remember this one. This is a good one to remember, that if you have a sum of numbers, let's say 1 through n, you add them all up, you get 1/2 n times n plus 1. Hopefully you remember that one. It's one of those things that that I do remember. And usually I cannot remember whether this was a plus or a -1, but I do remember that it has to be something that has to do with like 1/2 n squared, right? Because this is a little bit like taking the integral of k. So if you take the integral of k, you're going to end up with a 1/2 k squared, right? So it has to be something like 1/2 n squared, but there might be, you know, plus or -1 error. So then you just check your number, and you check your expression with k, sorry, with n is 1, and then you know that it has to look something like this. Okay, so that's just the sanity check. Now, second, when you look at this, you should see a sort of a similar structure. So this variable a runs from 1 through n minus 1, and this one runs from a plus 1 through n. So the average value of this is somewhere between a plus 1 and n. So this is a little bit like 1/2 n, and this, sorry, not 1/2 n. This one is 1/2 n, and this one depends on that. But you will end up with something that also needs to depend on n squared in some way, plus terms linear in n. Okay, so how do you do this? Well, so if you start with, let's say, 3 charged objects, then it's 1, 2, 3 pairs, right? Because you start with the 1, and then you have 2 terms, 1 and 2, and then the 2, you have one last term left, right? So for 3 charged objects, you have to do a sum of 2 plus 1. For 4 charged objects, you have to do a sum of 3 plus 2 plus 1. Okay, so it's like this, except you don't go up to n, but you go up to n minus 1. So it's 1/2 n minus 1, and then times n. There you go. There's another way to look at this problem, and that is to actually to not restrict this counter, but to say, you know what, I'm going to just take A and I'm going to let it run from 1 through n minus 1. And I'm going to take B and I'm going to let it run also from 1 through n minus 1. But I will count all my charged pairs double, and I should not self-count. So then you get n minus 1 times n minus 1 times 1/2 minus however many terms there are where A is equal to B, which is n minus 1. So you subtract that and you should get the same expression. All right. So Let's keep going. Where was my pair? Ah, here we go. Okay, so now that we have this written as a as a sum over pairs, we can also say that the sum of the Q B's over R A minus B is actually like the potential contribution to phi due to B that you then place our QA in. So in other words, we can actually write this as a sum over charged objects A that you place in a field. Oops. That you evaluate at those positions are A. Now, this is a very tricky position. That's why I wanted you to look at this expression first. Okay, so look very carefully. So first of all, we're basically treating these charged objects as independent objects that we place in an electric field, or sorry, the potential of an electric field that is formed due to all the other charged objects that that we're counting, right? But now, because we're no longer explicitly taking that potential out, we need to be really careful that we don't get terms where we're adding the charged interaction of the charged object with itself. So we'll get to that when we talk about the other version of this expression. Another thing that we have to pay attention to is this factor 1/2, because now, of course, we're no longer explicitly excluding charge pairs that we are already counting, so we're doing double counting. Okay. Now, if we have a potential that is due to a spherical charge distribution, sorry. So phi due to a spherically symmetric charge distribution then we can actually write that as phi of R. Now there are two contributions to this. There is the potential at that position where we are considering contributions to the potential due to charged objects that are closer to it. So, for instance, let's say we're I'm trying to draw here without making too much of a mess. Okay. Okay, so when we have this point here, this point R here, and we have a charge distribution that is only a function of R, we need to describe for instance, when we do the electric field or when we do the potential, we always need to consider stuff that is within this Gaussian sphere from the stuff that is on the outside of the Gaussian sphere. You should have seen these kind of expressions before, but that's the reason why when you write the potential for such a spherically symmetric charge distribution that therefore only depends on R and not phi and theta, it's going to be a sum of two terms, one for everything that's inside of this Gaussian sphere, and two, the contribution to all the stuff that is outside of the Gaussian sphere. Okay, so you'll therefore get a potential that is, this part is for inside, right? So because it's the integral from 0 to r. And then we're integrating that. dr. Let me put a prime here. There's a prime here. There's a prime here. And there's a prime there. Okay, so that's all the stuff that's on the inside. And then we also have the stuff that's on the outside. So this is for from r to infinity, 4 pi rho. And that's also a function of r prime. And then, oops, 4 pi r rho. So yeah. R prime, d r prime. Okay, so that's why when you get this potential, you get a sum of two terms. Okay, now we need to look very carefully at our primes, right? So shoot. Okay, we need to look very carefully at our primes, and when we want to now know the potential energy of such a charge distribution, so of basically this charge distribution's potential energy, where you consider all infinitesimal contributions of charge distributions rho, let's say here, and rho here, and then you integrate it not only over all the rows here, but also over all the rows here, you end up with not something that looks like this, but you end up with an integral, right? So that becomes an integral. So it will be 1/2 the integral, I'm writing this, oops, sorry, 1/2 the integral of rho and phi, okay? Where phi is this, and then rho is the other rho that you're integrating over. So it has the same structure as this one, where you consider a charge QA, and then you take all the charges QB and you measure the distance with respect to that QA by varying QB and the distance to that point QA. And then in the end, you also need to sum over the charge objects A. So we're doing the same thing here, right? We're saying, okay, we're taking the summer over all the objects A, and then the way they interact with the potential due to all the other charged objects that are encoded in that scalar potential. So we're doing the same thing here. So this scalar potential, of course, for this charge distribution also depends on the charge density rho. So now we will get a phi that is dependent on rho, and then we place another charged density dependence in there that is another rho, and we're going to get a double integral. So just like what we were doing here, instead of a double sum, we will get a double integral. But now we need to be really careful with our bookkeeping. So okay, now so the reason there's a 4 pi here is because we've already integrated our d theta and our d phi out, right? So we'll pick up another 4 pi here, because when we do this integral of 1/2 rho and phi, we are also integrating out our d theta and our d phi dependence. So we will end up with another 4 pi. So we'll end up with a 4 pi squared here. And then the first part of that integral, that's this rho, and from our spherical coordinate system, there's another r here, and then there's a rho, and then we integrate that. We add the second integral, this one, okay, and that goes from 0 to r, I already picked up my 4 pi. So I have an r squared, rho, and a dr. Okay, now let me make sure that I do my bookkeeping correctly. Yes, okay, so this is R2. This is R2. And this is R2. And then we're integrating R2 from 0 to R1. Okay, and then afterwards we are integrating R1, R1. And this one goes from 0 to infinity. So that's our first term, right? So all I did was I took this first term and I had my 1 over r here, but then I had an r squared from my spherical coordinate system. So that's why I only have an r1 here and not an r squared like I have here. Okay, so now I'm going to do the same thing, but now I'll use this term on the right. We also have a 1/2 4 pi squared here. And now we'll again repeat our first integral. Okay, dr1, r1. But now we'll have a squared here because no longer does this r squared cancel with the r that we had here that was being divided out. Okay, so we'll have this one. And now there's a rho, r1. And now we do the second integral. And that goes from r1 to infinity.